Hello everyone, my name is Nishar Ravindra Kokre. I am a chemical engineering student at Vishweshwara National Institute of Technology. My enrollment number is BT21CME033. My topic of presentation is Proton NMR. Proton NMR spectroscopy is essential in chemical structure identification. It reveals detailed molecular information. So it has significance in chemistry cannot be over understand, aiding in research and development. So this is the Proton NMR. So in this presentation, we will see the contents like introduction, 1H-NMR, principle, instrumentation, relaxation process, chemical shift, splitting of signals, NMR spectra and interpretation, and then references. So introduction to NMR. It is a study of absorption of radio frequency radiation by nuclei in a magnetic field is called NMR. Nuclear magnetic resonance spectroscopy is basically another form of absorption spectrometry. It involves change of the spin state or nucleus. When the nucleus absorbs electromagnetic radiation in a strong magnetic field, so the source of energy in NMR is a radio waves, which have long wavelength and thus low energy and frequency. So here we will see the proton NMR. So basically it's a type of NMR which we are frequently use, and I have selected this topic. It is a technique which is based on the absorption of electromagnetic radiation. In basically we are absorbing the electromagnetic radiation. And what's the frequency of that radiations are the 4 to 900 megahertz by the nuclei of the atom. So we are absorbing the radio frequency region of nuclei of atom from 4 to 900 megahertz. It is used to study a wide variety of nuclei as the 1H, 15N, 19F, 13C, and 31P. So these are the wide variety of nuclei which we are studying from basically from the proton NMR. The most common form of NMR base is hydrogen 1, nucleus or proton. So this is the most common form of NMR, shows how many kinds of non-equivalent hydrogens are in a compound. So it basically shows the non-equivalent hydrogen in the compound. Then another is equivalent H have the same signal while the non-equivalent are different, and as such may cause additional splitting. So it's a distereotopic effect is this is in a proton NMR. So here we will see the principle of proton NMR. So in a principle of proton NMR, protons in a different environment absorb at a slightly different frequency. So we are absorbing the protons in a different environment at different frequencies. So they are distinguished by NMR. So here we can distinguish them by the NMR. So they are at a different frequencies. The frequencies at which a particular proton absorbs is determined by its electronic environment. So we are frequencies at which particular proton absorbs is determining by its electronic environment. Then the size of magnetic field generated by the electrons around a proton determines where it absorbs. So basically the size of the magnetic field is generated is defining the where the electron where the proton is being absorbed. Then, in modern NMR, spectrometers use a constant magnetic field strength of B0, and then a narrow range of frequencies applied to achieve the resonance of all protons. And the only nuclei that contain odd mass numbers such as H1, C13, F19, P31, or odd atomic numbers such as 2H and 14N give rise to NMR signal. So this is overall principle of NMR working, and it will be used all across the types, and we are mainly focusing on the proton NMR. So the image explains the basic NMR spectroscopy. The image which we are seeing explains the basic of NMR spectroscopy. So without a magnetic field, nuclear spins are randomly oriented. When there is no magnetic field is there, they are oriented in randomly. When we apply a magnetic field, spins aligns into two states. So when we are applying the magnetic field, this randomly spins are aligned into two different spins. First will be the alpha spin, which is a lower energy spin, and another is a beta spin, which is a higher energy spin. So these are the orientation after the applying magnetic field to the randomly spins. Then nuclei absorbs a specific energy, which is a delta E, to move from alpha spin to beta spin state. So which is the basically delta is using for the moving from alpha spin to beta spin state. This energy is absorbed by the nucleus. When they are relaxed back, the release energy, which is detected by NMR, when they are relaxed, their energy, which will be get released by them, is detected by the NMR signals, and it is signals to study the molecular structure of it. So instrumentation of proton NMR. Basically, NMR instrumentation involves the following units. So I had defined the following units into the PPT, which are being the when we are basically defining the NMR instrumentation. So first will be the magnet to separate the nuclear spin energy state. There will be a magnet which will separate the nuclear spin energy state. Then there are two RF channels, one for the field frequency stabilization and one to supply RF irradiating energy. So these two type of channels working are like told. Then a sample probe, so containing coils for a coupling the sample with the RF field. It consists of sample holder, RF oscillator, sweep generator, and RF receiver. So then there will be a detector to process the NMR signals as usual, and a recorder to display the spectrum of recorded NMR. So these are the basic five NMR instrumentation involving units. Schematic diagram of an NMR spectrophotometer. Magnetic poles. Strong magnet creates a uniform and intense magnetic field required for aligning nuclear spins in the samples. So there is a magnetic poles. Then second will be the sample tube. The sample is contained in the spinning tube placed at the center of magnetic field. Spinning ensures uniform magnetic exposure and reduce distortions. Then third, radio frequency transmitter generate a transmits radio frequency waves to excite the nuclei in the sample, causing transitions between spin states. Then fourth, sweep coils and sweep generator. Sweep coils powered the sweep generator help adjust the magnetic field of RF frequency to resonate with different nuclei. Then fifth will be the radio frequency receiver and amplifier. Detects the energy emitted by the nuclei as they relax back to their lower energy state and amplifies the signal for analysis. Then the final and sixth will be the control console and recorder. Process processes the amplified signal and records the data to produce NMR spectra, which is used to interpret the molecular structure. So this is the schematic diagram explanation for NMR spectrophotometer. So relaxation process. Two kinds of relaxation process are there. First will be the spin-spin relaxation. So this takes place by transferring energy to neighboring nucleus. So here we are seeing the relaxation process. A nucleus in upper energy state can transfer its energy to neighboring nucleus by mutual exchange of spin. So this is the spin-spin relaxation. So another relaxation process is spin lattice relaxation. So what is the spin lattice relaxation? So it involves the transfer of energy from the nucleus in its higher energy state to the molecular lattice, and the energy is transferred to the components of lattice as the additional translational and vibrational rotational energy. And the process keeps the excess of nuclei in the lower energy state, which are necessary for NMR phenomena. Chemical shift. So chemical shift is the difference between the absorption position of sample proton and the absorption position of reference standard. So it is a basically difference between both the standard. One is the sample proton and the absorption position of reference standard. Then the position in NMR spectrum where signal occurs is called as a chemical shift. So position of NMR spectrum is known as a chemical shift. It indicates how far the signal is from the TMS reference peak. So what is the formula of chemical shift? So ppmd in this the shift from TMS in hertz divided by spectrometer frequency megahertz into 10 raised to 6. This is the formula for chemical shift and it gives into pp. So, splitting of signals. Here, each signal in NMR spectrum represent one kind or one set of protons in molecules. Then it is found that in certain molecules, a single peak, known as singlet, is not observed, but instead multiple groups of peaks is observed. So given example of C3CH2Br ethyl bromide. So we can see there are multiple peaks. It's found in a certain molecule. There are no single peak, which is a singlet, is observed. But instant, a multiplet is observed. So this is known as a splitting of signals. Then we will see the Pascal triangle. So what's the Pascal triangle? The number of neighboring edge. So if there is number of neighboring edge is 0, then the name of single is known as a singlet. And the representation is row is showing the 1. If n neighboring number of neighboring edge is 1, then it is known as a doublet. So representation as shown as a Pascal triangle 1 1. Then if there is a 2 number of neighboring edge, then it is known as a triplet. So representation is 1 2 1. If there are numbering of edge is 3, then it's known as quadrat. Then representation is 1 3 1 1, the row. And if there are 4, then 5 10, 1 4 6 4 1. If 5 6 10, then if 6 spectate, if 7 octet. So these are the Pascal triangle explaining this table. So now we will see H1 NMR spectra. H1 NMR spectra consist of signals originated from hydrogens or proton present in molecule. Only those hydrogens will give signals which are having different environment. So we are seeing the hydrogens having the same chemical environment will only appear as a single signal. So this is H1 NMR spectra. Now, we will see steps in 1H spectra interpretation. First, number of signals. Indicate how many different kinds of protons present. Then second, positions of signals. Indicate something about chemical shift, magnetic electronic environment of proton. Then third term is the relative intensity of signal. So what it indicates? The proportional to the number of protons present. Then fourth and final is the splitting of signals. Spin-spin coupling, indicating the number of nearby nuclei, usually protons. So these are the steps of H1 spectra interpretations. Now, a chemical shift table for different groups. So this is the uh, table of showing different groups with their chemical shift is the given into the ppm. So first RCH3, it's the methyl group, has the 0.7 1.3. Then there is R3CH 1.4 to 1.7. So there is showing different groups with their chemical shift. It is having the chemical shift in a ppm. So this also typically ranges for protons with variable chemical shift. So there are acids, phenols, alcohols, amines, amides, enols. So there are showing the ranges of protons with variable chemical shift. Then second is the dependency of chemical shift of C3HX on the element X. If the compound is C3HX, element X is if the F, then its electronegativity of X is 4, so chemical shift will be the 4.26. If the X is O, then the electronegativity of O is 3.5, so chemical shift will be 3.4. If the element is Cl, then electronegativity is 3.1, its shift is 3.05. If the element is Br, then electronegativity is 2.8, it's a 2.68. If the element is I, then the 2.5 shift is 2.16. If the element is H, electronegativity 2.1, it's the 0.23. So this is the dependency of chemical shift on the X element. So now we will see the example ethyl bromide NMR spectrum. Structure: the molecule contains a bromine atom attached to ethyl group CH2 CH3. Then chemical shift: peak 1, a quadrate at 3.4 ppm corresponding to 2 protons on CH2. The splitting is due to coupling with the 3 equivalent protons on CH3. So n plus 1 rule shows n is equal to 3. Then peak B, a triplet at 1.7 corresponding to 3 protons on CH3. The splitting arises from coupling with 2 protons on CH2. So n plus 1 rule, n is equal to 2. So this is also another example, 2-butanol, CH3CO, CH2, CH3. First A is singlet at 1.7, then quadrate at 2.5, and C is the triplet at 1.1. So this is the NMR of 2-butanone. So the another example of toluene, the molecule consists of benzene ring with methyl group is attached. So chemical shifts peak a singlet at 2.3 ppm corresponding to 3 protons of CH3 group. So it appears as a singlet because the protons on methyl group do not couple with others. Peak B, a multiplet at 7.2 ppm corresponding to aromatic protons on the benzene ring. The coupling pattern arises from spin-spin interaction among the aromatic hydrogens. So these are the all references I used to make my NMR PPT. I had several references across the internet and I had reference here. Thank you everyone for listening my presentation and thank you Verma sir for giving me opportunity to present this PPT and these are the all information about NMR spectrometry.